Good day, everyone. So my topic for today is about regression analysis, statistical inference. So the previous presenter discussed how to eat a regression equation to a set of points by using the least squares method. The purpose of this regression equation is to provide a good it to the points in the sample so that you can understand the relationship between a dependent variable and one or more explanatory variables. The entire emphasis of the discussion in the previous presentation was on finding a regression model that is the observations in the sample. So in my presentation, we take a slightly different point of view. So we assume that the observations in the sample are taken from some larger population. So for example, based on the given ebook, the sample of 50 regions from the Parmex drugstore example could represent a sample of all the regions where Parmex does business. In this case, we might be interested in the relationship between variables in the entire population, not just in the sample. Actually, there are two basic problems or issues we discuss in this topic. So the first has to do with a population regression model. So we want to infer its characteristics, that is, its intercept and slope terms from the corresponding terms estimated by least squares. We also want to know which explanatory variables belong in the equation. And there are typically large number of potential explanatory variables, and it is often not clear which of these do not best job of explaining variation in the dependent variable. So in addition, we would like to infer whether there is any population regression equation worth pursuing. It is possible that the potential explanatory variables provide very little explanation of the dependent variable. So the second issues or problem we'll discuss in this topic is prediction. So we touched on the prediction problem in the previous discussion, no? Primarily in the context of predicting the dependent variable for part of the sample held out for validation purposes. In reality, we had the values of the dependent variable for that part of the sample. So prediction was not really necessary. Now, we go beyond the sample and predict values of the dependent variable for new observations. And there is no way to check the accuracy of these predictions, or at least not right away, because the values of the dependent variable are not yet known. However, it is possible to calculate prediction intervals to measure the accuracy of the predictions. So, as what we have here, what is regression analysis? Okay? So, regression analysis, it is a powerful statistical regression, no, that allows you to examine the relationship between two or more variables of interest. Okay? While there are many types of regression analysis, at their core, they all examine the influence of one or more independent variables on a dependent variable. So the question is, what's a variable? So a variable is an object, event, idea, feeling, time period, or any other type of category you are trying to measure. There are two types of variables. Of course, we have independent and dependent variable. So, what's an independent variable? So, an independent variable is exactly what it sounds like. So, it is variable that is standalone and isn't changed by the other variables and you are trying to measure. So, for example, someone's age might be an independent variable. Other factors, such as what they eat, how much they go to school, how much television they watch, or aren't going to change a person's age. In fact, when you are looking for some kind of relationship between variables, you are trying to see if the independent variable causes some kind of change in the other variables or dependent variables. So therefore, what is dependent variable? So just like an independent variable, a dependent variable is exactly what it sounds like. It is something that depends on other factors. So for example, a test score could be a dependent variable because it could change depending on several factors such as how much you studied, how much sleep you go or you got the night before you took the test, or even how hungry you were when you took it. And usually we are looking for a relationship between two things. You are trying to find out what makes the dependent variable change the way it does. Many people have trouble remembering which is the independent variable and which is the dependent variable. An easy way to remember is to insert the names of the two variables you are using in the sentence and they want or in the way that makes the most sense. Then you can figure out which is the independent variable and which is the dependent variable. Again, independent variable causes a change in dependent variable, and it isn't possible that dependent variable could cause a change in independent variable. So for example, okay, time spent studying causes a change in test score, and it isn't possible that test score could change or could cause a change in time spent studying. We see that time spent studying must be the independent variable in the test score must be the dependent variable because the sentence doesn't make sense the other way around. Okay? So, how about the statistical model? So, to perform statistical inference in a regression context, a statistical model is required. That is, we must first make several assumptions about the population. Throughout the analysis, these assumptions remain exactly that they are only assumptions, not facts. These assumptions represent an idealization of reality, and as such, they are never likely to be entirely satisfied for the population in any real study. From a practical point of view, all we can ask is that they represent a close approximation to reality. If this is the case, then the analysis in this discussion is valid. But if the assumptions are grossly violated, statistical inferences that are based on these assumptions should be viewed with suspicion. Although we can never be entirely certain of the validity of the assumptions, there are ways to check for gross violations and we discussed some of this. So regression assumption. Because based on what we have here, there is a population regression line. It joins the means of the independent variable for all values of the explanatory variables. For any fixed values of the explanatory variables, the mean of the errors is 0. So take note of that. For any values of the explanatory variables, the variance or standard deviation of a dependent variable is a constant, the same for all such values. For any values of the explanatory variables, the dependent variable is normally distributed, and the errors are probabilistically independent. So, because these assumptions are so crucial to the regression analysis that follows, it is important to understand exactly what they mean. Assumption 1 is probably the most important. It implies that for some set of explanatory variables, there is an exact linear relationship in the population between the means of the dependent variable and the values of the explanatory variables. So, Figure 1, these explanatory variables could be original variables or variables you create such as dummies, interaction, or nonlinear transformation. And figure 2, it is the common to use Greek letters to denote population parameters and regular letters for their sample estimates. Okay, so hemosydacity, hemosydacity means that the variability of y values is the same for all x values. And heteroscedasticity means that the variability of y values is larger for some x values than for others. When we say homoscedasticity, it describes a situation in which the error term, or that is, the noise of random disturbance in the relationship between the independent variables and the dependent variable, is the same across all values of the independent variables. The errors have constant variance with the residuals scattered randomly around zero. If, for example, no, the residuals increase or decrease with the fitted values in a pattern, the errors may not have constant variance. To check this assumption, you should use a residual versus fitted values plot. Of course, this plot from the regression analysis for the fantasy football article mentioned based on the given example here in our ebook. The errors have constant variance with the residuals scattered randomly around zero. If, for example, the residuals increase or decrease with the fitted values in a pattern, the errors may not have constant variance. But if the errors are independent, there should be no pattern or structure in the log plot. In this case, the points will appear to be randomly scattered across the plot in the scatter shot fashion. If there is a significant dependence between errors, however, some sort of this deterministic pattern will likely be independent. How about heteroscedasticity? It is a hard word to pronounce, right? But it doesn't need to be a difficult concept to understand. Put simply, heteroscedasticity, also spelled heteroscedasticity, refers to the circumstance in which the variability of a variable is unequal across the range of values of a second variable that predicts it. So, the easiest way to detect non-constant error variance is through a visual inspection of a scatter plot. So, you create a scatter plot of the dependent variable versus an explanatory variable x and see whether the points vary across for some values of x than for others. You can also examine the residuals with a residual plot where residual values are on the vertical axis and some other variable or y or one of the x's is on the horizontal axis. If the residual plot exhibit a fan shape or other evidence of non-constant error variance, independence of residuals is usually in doubt only for the time series data. Okay? Assumption number 3 is equivalent to stating that the errors are normally distributed. Exact multicollinearity means that at least one of the explanatory variables is redundant and is not needed in the regression equation. And finally, assumption number 4, based on the given diagram or chart, requires probabilistic independence of the errors. Intuitively, this assumption means that information on some of the errors provides no information on the values of the other errors. So, for cross-sectional data, there is generally little reason to doubt the validity of assumption unless the observation are ordered in some particular way. And for cross-sectional data assumption, number 4 is usually taken for granted. However, for time series data, assumption 4 is often violated. And this is because of a property called autocorrelation. And maybe you are asking, what is autocorrelation? Autocorrelations refers to the degree of correlation between the values of the same variable across different observations in the data. Actually, the concept of autocorrelations is most often discussed in the context of time series data, in which observation occur at different points in time. So, for example, air temperature measured on different days of the month. For example, one might expect the air temperature on the first day of the month to be more similar to the temperature on the second day compared to the 31st day. If the temperature values that occur closer together in time are, in fact, more similar than the temperature values that occurred farther apart in time, no? Data would be autocorrelated. However, autocorrelation can also occur in cross-sectional data when the observations are related in some other way. In a survey, for instance, one might expect people from nearby geographic locations to provide more similar answers to each other than people who are more geographically distant. And similarly, students from the same class might perform more similarly to each other than students from different classes. Thus, autocorrelation can occur if observations are dependent in aspect other than time, because autocorrelation can cause problems in conventional analysis that assumes independence of observation, such as ordinary least squares regression. In regression analysis, autocorrelation of the regression residuals can also occur if the model is incorrectly specified. For example, if you are attempting to model a simple linear relationship but the observed relationship is nonlinear, or it follows curve or U-shaped functions, of course, then the residuals will be autocorrelated. How about inferences about the regression coefficients? We refer to theta and beta collectively as the regression coefficient. Again, Greek letters are used to indicate that these quantities are unknown and unobservable. There is one other unknown constant in the model. Of course, the variance of errors is important. There is one other unknown constant in the model. Okay? As I mentioned, again, the variance of the errors. Regression assumption number 2, as stated a while ago, state that these errors have a constant variance and the same for all values of the x's. We label this constant variance theta 2. Okay? Equivalently, of course, the common standard deviation of the error is theta. This is how it looks in the theory. There is a fixed set of explanatory variables, and given these variables, the problem is to estimate the theta and betas and the thetas. Okay? In practice, however, it is not usually this is straightforward. In real regression application, the choice of relevant explanatory variables is almost never obvious. There are at least two guiding principles, okay? Relevance and data availability. You certainly want variables that are related to the dependent variable. The best situation is when there is an established economic or physical theory to guide you. Typically, the most challenging part of a regression analysis is deciding which explanatory variables to include in the regression equation. The principle of parsimony is to explain the most with the least. It favors a model with fewer explanatory variables, assuming that this model explains the dependent variable most or almost as well as a model with additional explanatory variables. The sampling distribution of a regression coefficient, no? The key idea is again sampling distribution. Okay? Recall that the sampling distribution of any estimate derived from a sample data is the distribution of this state or estimate over all possible samples. And this idea can be applied to the least squares estimate of a regression coefficient. The result has three important implications. First, the estimate B is unbiased in the sense that its mean is B. The true but unknown value of the slope. If B's were estimated from repeated values, some would underestimate theta and others would overestimate beta, but on an average, they would be on target. Second, estimated standard deviation of B is labeled as B. It is usually called the standard error of a regression coefficient, or more simply, the standard error of B. And this standard error is related to the standard error of estimate SE, but it is not the same. Generally, the formula for SB is quite complicated and it is not shown here, but its value is printed in all standard regression outputs. It measures how much the B's would vary from sample to sample. A small value of SB is preferred. It means that B is a more accurate estimate of the true coefficient. Finally, the shape of the distribution of B is symmetric and bell-shaped. And the relevant distribution is the T distribution with n minus k minus 1 degrees of freedom. Standard error in regression, again, there are two quite different standard errors in regression outputs. The standard error of estimate, usually known at the top of the output, is a measure of an error you are likely to make when you use the regression equation to predict a value of y, inaccuracy of the individual coefficient. So this will be an example of a regression output for Bendrix example. This example is a continuation of the Bendrix manufacturing example from the previous discussion. So as before, the dependent variable is overhead and the explanatory variables are machine hours and production runs. What inferences can be made about the regression coefficient? The objective of this is to use standard regression output to make inferences about the regression coefficient of machine hours in production runs in the equation for overhead cost. So the solution, the output from StatTools regression procedure shown here, okay, this output is practically identical to regression outputs from all other statistical software packages. So the estimates of the regression coefficient appear under the label coefficient in the range B, of course, B18. So from here, no, from B18 up to B20. Okay. So these values estimate the true but unobservable population coefficient. And the next column, label is standard error. So as what we have here, standard error. Okay, shows the SB values, specifically 3.589487 is the standard error of the coefficient of machine hours, and 82.2.51 is the standard error of the coefficient of production runs. Each B represent a point estimate, no, of the corresponding, okay, based on this particular estimate of B1. The effect of the overhead of a 1 unit increase in machine hours is 43.53639.812. And you can be about 95% confident that approximately 36.357 to 50.715. Similar statement can be made of the coefficient of production runs in the intercept term. As with the population parameter, the sample data can be used to obtain a confidence interval for regression coefficient. So for example, the preceding paragraph implies that an approximate 95% confidence interval for the coefficient of machine hours extend from approximately 36.357 to 50.715. So, hypothesis test for regression coefficient and p-value. There is another important piece of information in regression outputs, no? The t-values for the individual regression coefficient. And these are shown in the t-value column of the regression output, and each t-value is the ratio of the estimated coefficient to each standard error. Therefore, it indicates how many standard errors the regression coefficient is from 0. So for example, the t-value for machine hours is about 12.13. So the regression coefficient of machine hours, 45.536, is more than 12 of each standard errors to the right of 0. Similarly, the coefficient of production runs is more than 10 of each standard errors to the right of 0. And a t-value can be used in an important hypothesis test for a regression coefficient. And to motivate this test, we suppose that you want to decide whether a particular explanatory variable belongs in the regression equation. A sensible criterion for making this decision is to check whether the corresponding regression coefficient is 0. If a variable coefficient is 0, there is no point in including this variable in the equation because the 0 coefficient will cancel its effect on the dependent variable. We take note that the test for whether a regression coefficient is 0 can be run by looking at the corresponding p-value and reject the equal 0 hypothesis if the p-value is small, say less than 0.05. The t-values for the regression coefficient allows you to see which of the potential explanatory variables are useful in explaining the dependent variable. But it is conceivable that none of these variables does a very good job. That is, it is conceivable that the entire group of explanatory variables explain only an insignificant portion of a variability of the dependent variable. Although this is an exemption rather than the rule in most real application, it can happen. An indication of this is that you obtain a very small R2 value because R2 is the square of the correlation between the observed values of the dependent variable and the fitted values from the regression equation. Another indication of a lack of it is that it is correlation. Of course, the multiple R is small. In this section, we state a formal procedure for testing the overall it or explanatory power of a regression equation. When the null hypothesis of no explanatory power is true, this F ratio has an F distribution with a K and N minus K minus 1 degrees of freedom. If the F ratio is small, the explained variation is small relative to the unexplained variation, and there is evidence that the regression equation provides little explanatory power. But if the F ratio is large, the explained variation is large relative to the unexplained variation. And you can conclude that the equation does have some explanatory power. Again, we need to take note that reject the null hypothesis and conclude that these X variables have at least some explanatory power. If the F value in the ANOVA table is large and the corresponding p-value is small, the null hypothesis is that all coefficients of the explanatory variables are 0. The alternative is that at least one of these coefficients is not 0. At first glance, it might appear that this null hypothesis can be tested by looking at the individual t-values. If they are all small, statistically insignificant, for example, then the null hypothesis of no, it cannot be rejected. Otherwise, it can be rejected. However, as you will see in the next discussion, it is possible because of multicollinearity to have small t-values even though the variables as a whole have a significant explanatory power. Okay, based on what we have here, no, the ANOVA table split this total variation into two parts. So the part explained by the regression equation as the part left explained. Okay. Then the unexplained part is the sum residuals, usually labeled SSE or sum of squared errors. The correct approach is to use an F-test. Okay. This is sometimes referred to as the ANOVA or analysis of variance. We say F-test, ANOVA is the same. Okay? Test because the elements for calculating the required F value are shown in ANOVA table for regression. In general, an ANOVA table analysis different sources of variation. In this case of regression, the variation in question is that variation of the dependent variable y, and the total variation of this variable is the sum of squared deviations about the mean and is labeled SST or sum of squares total. The F-test is normally procedure from testing whether the explained variation is large compared to the unexplained variation. Specifically, each of the source of variation has an associated degrees of freedom, okay, or df. For the explained variable or variation, df is equal to k, which is the number of explanatory variables. So for the unexplained variation, df is equal to n minus k minus 1, the sample size minus the total number of coefficient, including the intercept term, of course. The ratio of either sum of square to its degrees of freedom is called a mean square or MS. Okay. How about stepwise? Okay, so what is multicollinearity? So, recall that the coefficient of any variable in a regression equation indicate the effect of this variable on the dependent variable, provided that the other variables in the equation remain constant. Another way of stating this is that the coefficient represent the effect of this variable on the dependent variable. In addition to the effects of the other variables in the equation. In the Bendrix example, if machine hours in production runs are included in the equation for overhead, the coefficient of machine hours indicates that the extra amount machine hours explain about variation in overhead, in addition to the amount already explained by production runs. And similarly, the coefficient of production runs indicate the extra amount production runs explain about variation in overhead, in addition to the amount already explained by machine hours. Therefore, the relationship between an explanatory variable x and the dependent variable y is not always accurately reflected the coefficient of x. It depends on which other x's are included or not included in the equation. This is especially true when multicollinearity exists. So by definition, multicollinearity is the presence of a fairly strong linear relationship between two or more explanatory variables, and it can be make regression output difficult to interpret. In statistics, no, multicollinearity is a phenomenon in which one predictor variable in a multiple regression model can be linearly predicted from the others with a substantial degree of accuracy. Multicollinearity occurs when there is a fairly strong linear independent variables in a regression model are correlated. This correlation is a problem because independent variables should be independent. If the degree of correlation between variables is high enough, it can cause problems when you fit the model and interpret the results. Multicollinearity is a problem because it undermines the statistical significance of an independent variable. Other things being equal, the larger the standard error of a regression coefficient, the less likely it is that this coefficient will be statistically significant. In other way, to measure multicollinearity is the variance inflation factor or the VIF, which assesses how much the variance of an estimated regression coefficient increases if your predictors are correlated. If no factors are correlated, the VIFs or the variance inflation factor will all be 1 or will all be 1. Effect of multicollinearity actually. So, multicollinearity occurs when x's are highly correlated with one another. Okay? And it is a problem in many real regression application. Again, it prevents you from separating the influences of these x's on y. In short, it prevents you from seeing clearly how the world works. However, multicollinearity is not a problem if you simply want to use a regression equation as a black box for predictions. Suppose, for example, that you want to use regression to explain variation in salary. Three potential useful explanatory variation are age, no? Age, years of experience with the company, and the years of experience in the industry. It is very likely that each of these is positively related to salary, and it is also very likely that they are very closely related to each other. However, it isn't clear which, if any, you should exclude from the regression equation. If you include all three, you are likely to find that at least one of them is insignificant or yung high p-value, in which case you might consider excluding it from the equation. If you do so, this and R2 values will probably not change very much. The equation will provide equally good predicted values, but the coefficients of the variables that remain in the equation could change now considerably. Okay, so include exclude decisions. So look at a variable's t-values and its associated p-values. Actually, this will be the guidelines for including and excluding variables in a regression equation. Take note of it, especially if your proposal required to use a regression equation. Okay? Again, number one, look at a variable's t-value and its associated p-value. If the p-value is above some accepted significant level, such as 0.05, this variable is a candidate for exclusion. Again, if the p-value is above some accepted significance level, such as 0.05, this variable is a candidate for exclusion. Number two, check whether a variable's t-value is less than 1 or greater than 1 in magnitude. If it is less than 1, then it is mathematically fact that this will decrease and adjusted R2 will increase. If this value is executed from the equation, if it is greater than 1, the opposite will occur. Because of this, some statisticians advocate including or excluding variables with t-values less than 1 and including variables with t-values greater than 1. Again, majority of the statisticians advocate excluding variables with t-values less than 1, exclude, and include variables with t-values greater than 1. Okay? Number 3, look at t-values and p-values rather than correlation when making include-exclude decision. an explanatory or explanatory variable can have a fairly high correlation with the dependent variable. But because of other variables included in the equation, it might not be needed. And this would be reflected in the low t-value and the high p-value. And this variable could possibly be excluded also in a low t-value for the reason of parsimony. This often occurs in the presence of, as what we discussed earlier, multicollinearity. Number 4, when there is a group of variables that are in some sense logically related, it is sometimes a good idea to include all of them or exclude all of them. In this case, their individual t-values are less relevant. Instead, a partial f-test can be used to make the include-exclude decision. Number 5, use economic and or physical theory to decide whether to include or exclude variables and put less reliance on t-values and or p-values. Again, some variables might really belong in an equation because of their theoretical relationship with the dependent variable. In their low t-values, possibly the result of an unlucky sample should not necessarily disqualify them for being in the equation. Similarly, a variable that has no economic or physical relationship with the dependent variable might have a significant t-value just by chance. And this does not necessarily mean that it should be included in the equation. You should not use a software package blindly to hunt for good explanatory variables. And you should have some idea before running the package of which variables belong and which do not belong. Again, these guidelines can give contradictory signals. Specifically, Guideline 2 bases the include-exclude decision on whether the magnitude of the t-value is greater or less than 1. However, analysts who base the decision on statistical significance at the usual 5% level as in guideline number 1 and typically exclude a variable from the equation unless its t-value is at least 2 approximately. This latter approach is more stringent. Fewer variables will be retained, but it is probably the more popular approach. However, either approach is likely to result in similar equations for all practical purposes. In my previous experience, actually, you should not agonize too much about whether to include or exclude a variable at the margin. If you decide to exclude a variable that doesn't add much explanatory power, you get a somewhat cleaner equation and you probably won't see any dramatic shifts in R2 or SE. On the other hand, if you decide to keep such a variable in the equation is less parsimonious and you have one or more variable to interpret, but otherwise, there is no real penalty for including it. Stepwise regression. Multiple regression represent an improvement over simple regression because it allows any number of explanatory variables to be included in the analysis. Sometimes, however, the large number of potential explanatory variables makes it difficult to know which variables to include, and many statistical packages provide some assistance by including automatic equation building option. And these options estimate a series of regression equation by successively adding or deleting variables according to prescribed rules. Generically, the method are referred to as stepwise regression. It is a method of fitting regression model in which the choice of predictive variable is carried out by an automatic procedure. In each step, a variable is considered for addition to or subtraction from the set of explanatory variables based on some pre-specified criterion. Before discussing how stepwise procedures work, we need to consider a naive approach to the problem. You have already looked at correlation tables or indications of linear relationship. Why not simply include all explanatory variables that have large correlation with a dependent variable? And there are two reasons for not doing this. First, although a variable is highly correlated with a dependent variable, it might also be highly correlated with another explanatory variables. Therefore, this variable may not be needed in the equation once the other explanatory variables have been included. And this actually happens quite often. Second, no, even if a variable's correlation with a dependent variable is small, its contribution when it is included with a number of other explanatory variables can be greater than anticipated. Essentially, this variable can have sometimes unique to say about the dependent variable that none of the other variables provides, and this fact might not be apparent from the correlation table. This behavior doesn't happen as often, but it is possible. So for this reason, it is sometimes useful to let the software discover the best combination of variable by means of stepwise procedure. There are a number of procedures for building equation in a stepwise manner, but they all share a basic idea. So suppose there is an existing regression equation and you want to add another variable to this equation from a set of variables not yet included. At this point, the variables already in the equation have explained a certain percentage of the variation of the dependent variable. The residuals represent the part still unexplained. Therefore, in choosing the next variable to enter the equation, you should pick the one that is most highly correlated with the current residuals. If none of the remaining variables is highly correlated with the residuals, you might decide to quit. This is essence of stepwise regression. However, besides adding variable to the equation, a stepwise procedure might delete a variable. This is sometimes reasonable because a variable entered early in the procedure might no longer be needed, given the presence of other variables that have entered subsequently. Many statistical packages have three types of equation building procedures. They have forward, backward, and stepwise. A forward procedure begins with no explanatory variables in the equation and successively adds one at a time until no remaining variables make a significant contribution. A background procedure begins with all potential explanatory variables in the equation and deletes them one at a time until further deletion would do more harm than good. And finally, a true stepwise procedure is much like a forward procedure except that it also considers possible deletion along the way. All of these procedures have the same basic objective: to find an equation with a small SE and a large R2 or adjusted R2. There is no guarantee actually that they will produce exactly the same final equation. But in most cases, their final results are very similar. The important thing to realize is that the equation estimated along the way, including the final equation, are estimated exactly as before by least squares. Therefore, none of these procedures produce any new results, and they merely take the burden of the user of having to decide ahead of time which variables to include in the equation. Another thing, of course, in stepwise regression is the option to let the statistical software build the regression equation automatically makes the various version of stepwise regression very popular with many users. However, keep in mind that it does nothing that can be done with multiple regression, where the choice of excess is specified manually, and sometimes a careful manual selection of the excess to include is better than letting the software make the selection mindlessly. Stepwise regression has its place, but it should be a substitute for thoughtful analysis. While stepwise linear regression, it is a method of regressing multiple variables while simultaneously removing those that aren't important. It essentially does multiple regression a number of times, and each time removing the weakest correlated variable. What is outlier? Okay? So an outlier is an observation that lies an abnormal distance from other values in a random sample from a population. Okay? In a sense, this definition leaves it up to the analyst or a consensus process to decide what will be considered abnormal. These points are often referred to as outliers. The most effective way to find all of your outliers is by using the interquartile range or the IQR, because the IQR contains the middle bulk of your data, so outliers can be easily found once you know the IQR. Okay? Potential characteristic of an outlier, it has an extreme value for at least one variable. It has value of independent variable is much larger or smaller than predicted by the regression line, and its residual is abnormally large in magnitude. Its residual is not only large in magnitude, but this point tilts the regression line toward it. And its values of individual explanatory variables are not extreme, but they fall outside the general pattern of the other observation. Okay, based on what we have here, okay, outliers that tells the regression line. So once outlier have been identified, as you can see here, there is still the dilemma of what to do with them. In most cases, the regression output will look nicer if you delete outliers, but this is not necessarily appropriate. If you can argue that the outlier isn't really a member of the relevant population, this is then it is appropriate and probably best to delete it. But if no such argument can be made, then it is not really appropriate to delete the outlier just to make the analysis come out better. Perhaps the best advice in this case is that advice we gave in the discussion a while ago. Run the analysis with the outliers and run it again without them. If the key outputs do not change much, then it does not really matter whether the outliers are included or not. If the key output change substantially, the report or the results both with and without the outliers along with the verbal explanations. Okay, we have a violation, progression, and assumption. The second regression assumption states that the variance of the errors should be constant for all values of the explanatory variables. This is a lot to ask, and it is almost always violated to some extent. Fortunately, mild violations do not have much effect on the validity of the regression output, so you can usually ignore them. However, one particular from non-constant error, okay, variance occurs fairly often and should be dealt with. This is the fan-shaped scatter plot of amount spent versus salary. As salary increase, the variability of amount spent also increases. Although this fan shape appears in the scatter plot of the dependent variable amount spent versus the explanatory variable salary. It also appears that in the scatter plot of residual versus fitted values if you regress amount spent versus salary. If you ignore this non-constant error variance, the standard error of the regression coefficient of salary is an accurate and a confidence interval for this coefficient, or a hypothesis test concerning it can be misleading. A pan shape can cause an incorrect value for the standard error of estimate, so that confidence interval and hypothesis test for the regression coefficient are not valid. A logarithmic transformation of y can sometimes cure the pan shape problem. So this logarithmic transformation is not a magical cure for all instances of non-constant error variance. So for example, it appears to have introduced some curvature into the plot in this figure, no, 11.18. Okay? However, as we discussed in the previous discussion, when the distribution of the dependent variable is heavily skewed to the right, as it is open, is the logarithmic transformation is worth exploring. Okay, normality of residuals. Addressing non-normality, okay, or residuals, or what we call heterozygoticity, we have 8 distinct methods suggested to address non-normality, which we organize into a new taxonomy according to whether the approach. Letter A, remains within the linear model. Letter B, changes the data. And letter C, treats normality as informative or as a nuisance. We just try to recall, no, that the assumption of normality can be relaxed when sample size n is large enough. The errors need not follow a normal distribution because of the CLT. Regardless, no, of the distribution for E, the CLT assures that the sampling distribution of the estimate will converge toward a normal distribution as n increases to infinity when are independent and identicality distributed is finite or finite. When non-normality is E is observed, two assumptions in the linear model are potentially unmet. The linear model in its special cases tend to be the starting point of data analysis in the behavioral science. Open, researchers' foundational training in methodology does not extend beyond the linear model, inadvertently creating a pedagogical gap because of the ubiquity of observing non-normal residuals E in practice. Non-normality in E suggests potential violation of the model assumptions about E, which can result in an accurate result, or the bias estimate and inaccurate inference. Okay? So, again, with the 8 distinct approaches have been suggested, but in-depth coverage of these approaches was severely lacking. Of course, there are certain books written from the frequent perspective of probability, but Bayesian analogs to modeling non-normality are gaining traction. We organize the identified methods into a new taxonomy according to 3 characteristics pertaining to whether methods continue within the linear modeling framework, whether the data are modified, and whether non-normality is considered a nuisance or informative. And we have, of course, what we call autocorrelation. Autocorrelation refers to the degree of correlation between the values of the same variable across different observations in the data. The concept of autocorrelation is most often discussed in the context of time series data in which observation occurs at the different points in time. Again, air temperature measured of different days of the month. So for example, one might expect the air temperature of the first day of the month to be more similar to the temperature of the second day compared to the 31st temperature. However, autocorrelation can also occur in cross-sectional data when the observations are related in some other way. In a survey, for instance, one might expect people from nearby geographic location to provide more similar answers to each other than people who are more geographically distant, similar from the class might perform more similarly than other students from different classes. Thus, autocorrelation can occur if observations are dependent in aspects other than time. Autocorrelation can cause problem in conventional analysis that assumes independence of observation. Okay, the regression approach for predictions. Okay, so prediction errors for an individual value and the mean. So using regression to make predictions doesn't necessarily involve predicting the future. Instead, you predict the mean of the dependent variable given specific values of the dependent variables. For example, we'll use one independent variable to predict the dependent variable. We measure both of these variables at the same point in time. Photograph of a crystal ball that a physics uses to make predictions. Physics predictions are things that just pop into mind and are not often verified against reality. Unsurprisingly, predictions in the regression context are more rigorous. We need to collect data to relevant variables, formulate a model, and evaluate how well the model fits the data. The general procedure for using regression to make good prediction is the following. Number one, again, before I forget, this will be the general procedure for using regression to make a good predictions is number one, research the subject area so you can build on the work of others. And this research helps with the subsequent steps. Number two, collect data for the relevant variables. Number three, specify and assess your regression model. And the last is if you have a model that adequately fits the data, use it to make predictions. While this process involves more work than the specific approach, it provides valuable benefits. With regression, we can evaluate the bias and precision of our predictions. How? Bias in a statistical model indicates that the predictions are systematically too high or too low. Precisions represent how close the predictions are to the observed values. When we use regression to make prediction, our goal is to produce predictions that are both correct on average and close to the real values. In other words, we need prediction that are both unbiased and precise. Based on what we have here, the standard error of predictions for a single y is approximately equal of the standard error of estimate. A prediction error is the failure of some expected event to occur. Okay? Prediction error in the case might be assigned a negative value and predicted outcomes a positive value, in which case the AI would be programmed to attempt to maximize its score. The equation of calculation of percentage prediction error, of course, the percentage prediction error equals measured value minus predicted value, measured value multiplied by 100, or percentage prediction error is equal to predicted value minus measured value measured times 100. And similar equation has been widely used. So, so in this chapter, no, about the regression analysis, no, you have see how useful regression analysis can be for a variety of purpose or for a variety of business application, and how statistical software such as stat tools enables you to obtain relevant output, both graphical and numerical, with very little effort. However, you have also seen that there are many concepts that you must understand well before you can use regression analysis appropriately. Given the user-friendly software is available, it is also too easy to generate enormous amounts of regression output and then misinterpret or misuse much of it. At the very least, you should, of course, be able to interpret the standard regression output, including statistics on the regression coefficient, summary measures such as R2 and SE, and the ANOVA table. We need to know what to look for in a many scatter plots available. We need also to know how to use dummy variables, interaction terms, and nonlinear transformation to improve a fit and be able to spot clear violation of the regression assumption. However, we haven't covered everything. Indeed, some entire books are devoted exclusively for regression analysis. Therefore, you should recognize when you don't know enough to handle a regression problem, such as non-constant error variance or autocorrelation appropriately. In this case, you should consult a statistical expert. So we have here some summary of key terms. We have statistical model, error, homozydasticity, heterozydasticity, parsimony, standard error of a regression coefficient or S sub B, confidence interval for a regression coefficient, and this will be some explanation, no, in Excel applications. T-value for t-test and regression of coefficient. We have hypothesis, test for a regression coefficient. Again, this will be the explanation and the statistical Excel application. We discussed already the ANOVA table for regression, multicollinearity, include-exclude decision, and stepwise regression. Outliers, influential point, or a point that can tilt the regression line. Autocorrelation of residuals, Durbin-Watson statistic, point predictions, standard error of predictions. And this will be my references. So thank you everyone and good day again.